I'm really excited about our conversation today. We're going to be unpacking a whole bunch of things and kind of discussing, how the ecosystem and how the industry is kind of shaping up over the coming years.
So each person had to have their own index, because if you deleted a message and I didn't, figuring all this out was almost impossible. So 20 times, 3 times the volume of messages per day, which was about 150 million messages or so, I think, was being exchanged by people. That's like a lot, right?
The systems that you were involved in building out at Facebook were Cassandra and HP.
Yes, we built an open sourced Cassandra back in Facebook. This was, even the name choice was interesting.
The tooling in the ecosystem, from the point of view of vendors like Yugabyte, but also from the point of view of API layers like Hasura, is to make that transition easy as well. To say that, start off with that Postgres, and you're noticing that one model or one set of models are going crazy and they need that scale out. Making that migration easy to say, can I keep like 90% of my tables in Postgres and not have to worry about that migration, but take the 10% and move that into Yugabyte, and then start putting my new workload there. That starts to become a feasible thing to do, right? And I think the industry is going to kind of keep moving there.
Thank you so much for everyone for joining today. We're excited to have Karthik Ranganathan, and I still messed it up even though we practiced, CTO and co-founder of Yugabyte, and Tammy Gopal, co-founder and CEO of Hasura. Without any further ado, I'm gonna hand it over to our speakers.
Hey everybody, great to be here. Thank you, Karthik, for joining us today. And thanks everyone for maybe before we get started, would love to do a round of personal introductions. Karthik, if you'd like to just maybe do a quick intro, what you've been up to before Yugabyte, at Yugabyte, and so on, would be great to hear.
Sure. Happy to. So mostly been an engineer most of my career. So right here I'm the CTO, and sometimes even I don't know what that means, but it depends on the day, but it's mostly technical, which is actually fun. And myself, a couple of my co-founders, we started the company early 2016. And before this, I was at Nutanix. I've been working on distributed systems for a while. It seems I just can't get enough of the pain of distributed systems. So building them, running them, the whole 9 yards. So before this at Nutanix, I was building distributed storage systems. So this is like EBS for private cloud. So you just install software on a bunch of commodity machines, and it behaves like an EBS, concerted and works together. And before that, I was at Facebook for about 6 years working, and that's where I met my co-founders. Most of us that worked on building distributed databases at Facebook, we pretty much ended up making the founding team of Yugabyte, and from the engineering side. So we started. So the funny incident there, this was back in 2007 when I joined Facebook, is the world was a very different place. No cloud, no SSDs, no microservices, no Kubernetes, no nothing. It just seems like, what the hell was there? There was a lot of stuff, but it just feels like it now. None of the terms we use seem to be there back then. Anyway, so at that time, there were no distributed databases, and open source databases were definitely not a thing. There was MySQL and Postgres, and people always thought, at least I always thought, okay, they've always been open source, so that's it, right? There's nothing more to say to it than that. And we built databases at Facebook to distribute data, query processing, etc. Facebook had a you run what you build policy. So they probably did it from the application perspective. Little did they know about the infrastructure and what it entails. But we got paged at 3 a.m. and absolutely hated it. And then we realized, oh my God, we learned so much about building the database. So then I guess we really liked it after it was done. And then we said, why don't we do this again? And then we got together, and we're back into it and getting paged at 3 a.m. whatever. Right? So anyway, that's the fun little journey. So, but mostly been in engineering, just love data, distributed systems, and cloud native, everything.
That's awesome to hear. And I think the systems that you were involved in building out at Facebook were Cassandra and HP.
Yes, we built an open sourced Cassandra back in Facebook. This was, even the name choice was interesting. With we didn't know it would take off. Like I said, open source database is not a thing back then. So we built this pure storage query processing system, something like that. It was a mouthful and nobody could repeat it a second time the same way. And so, the management said, guys, you got to give it a name. And the three of us working on it, nobody could be bothered to give it a name. It's like, dude, what's in a name? It's like boring stuff. So, finally, somehow they caught me and said, dude, you got to name it. You look like the weakest link here. So you got to name it. And I'm like, okay, man, who's going to spend time naming a database? So I figured like, okay, anything worth naming has got to sound like Oracle, something after Oracle. So I looked up what oracles were known in the Greek mythology, and those guys didn't do a very good job. They should have put more oracles out there. Anyway, Delphi, Oracle of Delphi was the most famous. Delphix was taken, clearly couldn't do it. Okay, and there's only one other oracle I could even find, which was Cassandra. Well, apparently whatever she said was true, but nobody believed it. We're like, what the hell, let's name it. And then it just took off in open source and they eventually consistent. And people are like, it's living true to its name and it has all the sense to it. Anyway, it wasn't really so much thought process behind it, but yeah, so.
That's awesome. I did not know about that. I did not know about that the way that the name came about, but it makes sense. I think, and kind of also on that theme of things that have changed quite a bit is also, I think, just the amount of kind of internet penetration, right? Handheld devices, mobile, web, right? And, all of like that entire ecosystem also has changed, right? Which is it's fascinating.
Yeah.
But yeah, I think it kind of teeing up into our conversation today, what we were kind of planning to unpack today was thinking about, what it would take to build an application today, right? That is quote unquote Facebook scale, and how that's different today, and perhaps even fundamentally different today. Even approaching that kind of a product build today would be fairly different from 10, 15 years ago, when a lot of these technologies and a lot of the movement in the ecosystem, the way that users behave, etc., was very different, right? And I think kind of zooming in two particular aspects to talk about those changes, right? One, I think, of course, on the kind of centralized database side, on the OLTP side of things, and how that's changing, and then second, on kind of the edge side, which is also gone through a fairly drastic change, right? And so maybe kind of unpacking that on the centralized data side of things, right? Karthik, if you think about like how today one would approach building a product that required this kind of centralized transaction storage, this kind of OLTP engine for a part of the application, right? What's different? Like, what has changed, and what has kind of changed technically, or what are the changes in the ecosystem, and what are also kind of some of the requirements that are now just things that we want from the very get-go, right? As opposed to having to build in-house, right? So what is that like?
Yeah. I think maybe I'll explain this in the maybe context of a journey, a story of what really happened. Like, for example, as we built this at Facebook, and just every time I say this is what we did, we can talk about what is it that we would do now. And it won't take very long, right? So I won't put you guys to sleep. So like back in 2007, right? Like, why did we even build a database, right? We actually analyzed a lot trying not to build a database because why do it? The problem that we first had was Facebook had, if you remember back then, there was a Facebook messaging service inside Facebook where you could send messages. It's not the messenger of today. Think about it like an email-like service, right? Like, so I want to send you a message. I go to the site and type something and hit send, and it behaves like an email. There's threading and just like email, right? And there was chat. It was held in memory, and there was no SMS back then. It was 2007, right? So people we didn't have that much penetration. It's hard to imagine, but yeah, that's how it was. So the problem that we were trying to solve was a ton of users were saying, guys, we over time have accumulated a lot of messages and we can't search through them. So how do we search through them? Now, if you think about how Facebook was architected back then, obviously there were no, forget distributed SQL databases. There were no distributed databases, period, right? Like you had MySQL, you had Postgres, and then you had Oracle SQL Server DB2, which, wasn't in the Facebook ethos of doing because it'd get too expensive. So that's all there were. So I'm not talking about rack and Exadata. They were really not choices. So we wanted to build it on commodity hardware. So The way Facebook was architected, it was a giant, you could think of our user serving system as a giant distributed SQL database. It was MySQL, it was sharded, it had, you could do some transactions across, but it was enforced by another tier to maintain consistency of data. So this was all this giant machinery. But it was running on higher quality hardware like SAS drives and like, higher quality, higher RPM hard disks. I don't know, I shouldn't even say that. I'm probably dating myself saying all this stuff. But anyway, so higher quality disks and a little more specialized machines. And we'd have an operational team take care of it, and replication was carefully managed and all that. Now, why anybody didn't want to build search was like, the reason is if I send you a message and I write, say, 20 words, right? It's not a very big message. That's one message for you, but that's 20 entries into the search index, because it's like you got to put every word for every message. So it simply explodes. So 1:20 is the conversion ratio. If your average message size is 20, the average number of recipients per message was, I think, about 3. So each person had to have their own index, because if you deleted a message and I didn't, figuring all this out was almost impossible. So 20 times 3 times the volume of messages per day, which was about 150 million messages or so, I think, was being exchanged by people. That's like a lot, right? So, and how many people read this? You go and search once in a while, but you don't care. So it felt like we were building a system that would be very expensive for being barely used, but it's very useful, right? So we said, okay, look, we got to think about it a different way. And then we came up with building this database that would be eventually consistent. We had to compromise on something in the CAP theorem, but it would be easy to run across data centers. So that gave birth to Cassandra, right? So if somebody complained about their messages, fine, let's go get it from MySQL, reindex it, and you're done. Then Facebook evolved. They said, like, look, my app is now changing. Everybody really likes it. It's taking off. It's getting more penetration. I want to make messaging even simpler on Facebook. And that's when Mark Zuckerberg, a bunch of others, they thought of the Messenger product, what you know as Messenger for today. They said, this makes no sense. If I want to send Tanmay a message, I need to know, hey, is Tanmay more likely to respond through chat or through the messaging system or through SMS? Just too complicated, right? Why don't I send Tanmay a message and Tanmay can pick his preference of how to receive the message? And that makes it simple, right? Whatever the preference of the person, that's just taken care of, because I want to tell him something. He needs to know how to receive it, right?
Right.
So that was the big vision, product vision, simple thing to say. But when you come to infrastructure now, we had like a ton of chat messages, but it was all in memory. We had these 150 million messages. And to make things worse, we wanted to make it work like SMS. So no subject, just one-on-one threading and just a group of people doing stuff. So the problem here, if you put yourselves in that shoe for a second, is you don't know what to expect when you release this thing. How many people are going to send how many messages? Because everything is built around that. You just don't know. So what we knew was we couldn't say no to messages, because they would spike at any time. They would spike immediately. They would spike a year later. And to make things worse, at least as from the perspective of people building infrastructure, it's like, you product guys are doing send on enter. What is that? You hit enter, it sends a message. Do you know what it means to the backend? And you have to actually write the message before delivering it. It was just a pain, right? So at least from the database perspective, it's just putting it through the, so we said, okay, we got to now rethink this CAP theorem thing. Fine. So we went and said, consistency is important. We can't have a message disappear or 2 of a message appear. All of that is going to be bogus. We can't go fix it up from somewhere. This has to be the system of record. So then we ended up building HBase, right? Now, HBase was a CP database, consistent and partition tolerant, but not highly available, which meant on failures, it would be a 3-minute failover. And we were okay with that. We had to make some compromises because, who knows how much this thing is going to take off. Let's deal with it later. So we went ahead and built that. And we said, if we can handle so much of write volume, we sure as hell can handle the search index also. So we moved the search index and the messages, and that product itself, the move itself was pretty complicated. And then the inbox changed to becoming friend and friend of friend oriented rather than just an inbox of stuff. So it changed like how you think of a modern, and we wanted to go and become carrier grade, which is like just like your SMS as messenger had to work as well, right? So that means high uptime, no downtime. You can't say any reason why it went down. Sure as hell, not everybody's using it. That's why it went down. You can't say that. You can't be beaten by your success, right? So all of that, right? And every message had to be written before you acknowledge, because writing in memory meant messages could disappear. Okay, so when we opened the clock, the migration took a few months anyway, but the number of messages, like if you remember the old system, 150 million to 20 billion per day, right? That's where the system like kind of settled as it was fully rolled out and people got used to the usage. And there's no way we would have predicted what that number was. We had to be ready to move on a dime, right? Like, and And so the big problems there were like, firstly, we had to go and address how do you get the machines and drip them in and procure them and put them in the right data centers and get the software running, just a lot of complexity around that. How do you make sure that as machines were filling up and usage was going up, how do you add machines and keep them ready and so on and so on, right? So let me pause, for example, just for that portion of the journey. If you now forward to today, right, what happens? Well, distributed databases are not uncommon. A bunch of them out there, and probably the harder problem is choosing the right one. Like, definitely not is there one, because back then there were none, right? So we had to build a couple. And then if you look at your machines, well, back then for Cassandra, I distinctly remember we were like, hey, how many machines should we order for this thing? I don't know, but just do 50 machines. Sure, we'll deal with it. If we don't need that many, somebody else will deal with it. But let's order it even before we built the database. That's because the machines would take 9 months to 1 year to come, right? And we said, like, who knows what this software that we built, how many machines it would take to run the 150 million? No idea, but we would deal with it. If you waited to build it and get that idea, well, it'll take you a year from then to release, and you're just waiting on machines. It's too late. So that's not a problem anymore. You have an API 6 minutes later, 4 minutes, whatever later, you have your 100 machines if you want it in whatever region you want. That makes it really simple. Infrastructure as code wasn't a thing. We had to get people to rack and stack it. So the machines would be there, but they would not be there for you because somebody's dealing with it. And we'd be like, okay, 1 week. Oh no, it delayed by 1 more week because somebody tripped on a cable on the other side. Sure, 1 more week. So you had to deal with all this stuff. And now you don't even care. It's just somebody deals with it, right? So, and then you would run into breaking in the machines. I don't even people know what that means. Like, you could end up with, like, of the 100 machines you ordered, maybe 50 machines that came in one batch had bad hard disks or bad CPU or bad something else. And you had to do test runs before you put them in production. So, all of this gets abstracted away, right? And finally, like, scale, right? Like, all databases now are thinking about scale. Now, when I say scale, some people think I don't have 50 petabytes of data to store today, right? And I will never have 50 petabytes of data. But that's not what scale is. Scale is anything that outruns a single machine, right? You have a simple 16 or 8 core machine, and you can no longer deal with it to serve your data. You need more. And maybe after a month or after a day or whatever it is, you don't need that extra compute. You need to bring it back to 8 cores, right? How do you deal with this type of change in scale, even at the smaller end of the spectrum? How do you deal with that? That's very important, because your service will build up credibility over time, but you don't want to be in a situation where, great, everybody loves it, but it's going to take me 9 months to rewrite it to shard. That's a bad place to be. So those are some of the changes. I think broad brush strokes, those are some of the changes. As we go even further into the life cycle, I can talk about more things like, how do you deal with security? How do you deal with upgrades? How do you deal with data center decommissions, machine type changes? But anyway, it gives you the idea, right? These things have to be built into the data layer.
Yeah, no, that's awesome. That makes a lot of sense. And it's hard to imagine that this was the situation just like barely 10 years ago. Right?
Barely 10 years ago, yes.
Yeah, now you don't even think about this kind of stuff. I think kind of zooming into that particular piece about especially when we're thinking about how to approach this idea of what distributed database to choose, right? And what kind of trade-offs to think about. That trade-off that you had at the time, that when you're talking about Cassandra, where you traded off consistency for availability, and HBase, which was exactly the opposite, right? What does that choice matrix look like today, right? Or today for an architect, right? How would architects today think about the way to think about their workload and to map that to different dimensions of what distributed databases can do?
Yeah. This is a pretty critical question, right? Because distributed can mean many things to many people. So I think, and obviously we built a third database after having built 2 databases because, we were bored, but no, not really. But if you think about it, I think I guess sometimes the simple things strike you only after you've done a lot of work and been bitten pretty badly, right? Such is life, probably in many ways, other than just databases or distributed data. But anyway, that's a story for another day. We built Cassandra with eventually consistent because it was just way easier to deal with it across data centers. It's very simple to handle it. It would do its best effort repair. If people complain, sure, we can go and do this. Or we can go and index data. And we didn't want people to complain all the time. I mean, what good is it? Like, I think at the time there were about 1 billion users on Facebook Plus, and there were hundreds of millions of monthly active. So there's a lot of users, right? So if for example, the system was eventually consistent, like as in data was not always appearing, say even 1% of the time, that's 100 million users complaining on a steady state basis. all the time.
Mhm.
So that means 100
Mhm.
million users aren't seeing the right messages, and that's a very sucky product. So
Right.
we cannot be eventually consistent too often, right? It has to be pretty
Mhm.
rare. Now, when we move to fully consistent, that's the AP with a trade-off on,
Right.
right?
Right.
Now, when we moved to fully consistent, because we knew that's a problem because of the number of tickets we had to fix, even if it was a small percentage, we moved to a CP database and traded off A and availability. And what that meant was when a machine failed, it would take about 3 minutes for that data to get remastered elsewhere.
Right.
Okay, for first thing. And the second thing was, and if you guys know how HBase works, there's HBase, there's HDFS, there's the name node, there's Zookeeper, there's like 15 other systems you have to deal with. And these systems are not truly built for the cloud. Okay. And what I mean by that is in a cloud, you have a notion of zones and regions, right? And remember, all of these databases, including Mongo, all of these databases were built in the pre-cloud era, right? That means you didn't know SSDs were going to be the stock things. SSDs were barely struggling to run. I remember Facebook experiments when SSDs wouldn't work and they'd keep iterating with the companies building the SSDs. There was no notion of zones and regions, right? It was not public cloud architecture. It was not, and we inside Facebook used to build our own data centers, and we built nearby and far away data centers, what are called zones and regions now. And it was just evolving, right? And so some of the issues we had faced were somebody would trip over a cable and about 60 of your 100 machines would go down. No database is going to survive that, right? So
I thought that was a joke. This is seriously.
No, it happened seriously.
Okay,
it seriously happened. Yeah, I don't even blame the poor person because he's in an ocean of machines and he's got to turn somewhere. So yeah, probably like if it was me, I would have tripped over many more cables, and so they shouldn't let me in. But anyway, that's a different story. But the thing is, you incur downtime for the most crazy, bizarre reasons, right? Like you cannot do anything about it. So the multi-zone type deployment is really to ensure your availability is high. In fact, the silly thing is we chased this 5 nines throughout our HBase deployment, and we reached our 5 nines. And then we found, look, if you have 1 billion users, you can have 1 million users down for a week. It's not a big deal. You still achieve your 5 nines because you're dividing that million outage by 1 billion users. So what gives, right? So then we said, look, this is a bogus metric. We can't really go after that. We have to go after number of messages failing and a different type of metric, right? So some of these trade-offs, and what we finally realized was it all came back to the CAP theorem, which is it's because your failover time is 3 minutes at minimum. Right, with synchronous replication, and anything else is even worse and loses data. So we said we have to break it at that layer. And so at Facebook itself, we were looking at how do we build the next generation system. And halfway through that, we left to Nutanix, etc. And Yugabyte is built along the same lines as what Facebook ended up building. It's called ZippyDB. And in fact, we have some of the ZippyDB folks at Yugabyte too. The idea there was, how in an AP system like Cassandra, the inconsistency is a very small percentage. But in a CP system, why is the availability so big? Can we make the availability really, really small, right? So then your availability doesn't quite impact you as much on the database tier because you're going to have unavailability everywhere, right? So your app can't connect to the gateway can't connect to the app. So every stage can introduce something. You don't need to be the biggest, that's all. You just need to be smaller or equivalent compared to the others, and you're okay, you've built a practical system, right? So here we kind of have a system where it's a 3-second to failover. Right, from between when a node dies in a multi-zone single region type deployment. So that's a good trade-off, but it's perfectly consistent. So you don't have to fix up your data. The second thing we observed was, throughout our careers of, we finished Cassandra, we finished HBase, where in fact in the next company, people still come to us and say, hey, why don't you just build that secondary index that's like super useful in Cassandra? I can't really read my data in another way. And we had to tell them, look, at the time you were just happy we were giving you anything distributed. And, that was that, at least that's what people told us inside Facebook. And now suddenly it's like, I want to build this index. I want to drop that index. I want to join this data. How about just a small table, not a big deal, small join. Can you please do it? So we were like, oh, no, that's not built that way. So then we realized, look, relational databases are the standard. Why are we deviating from that? So why are we just giving people a shock, right? And so, and so the trade-off now I would say that people have to do is really think about scale on demand, right? And predictable scale on demand, not like you have to do so much work that everybody's burnt out at the end of the scale. Right? The system has to do with itself. It has to be graceful. It has to tell you when it's done. It has to be consistent. It has to be highly available. Like you have to think about those. These are some of the things to think about, right? And of course, SSD becomes another important thing because no one's really doing OLTP on hard disks anymore.
Got it. Makes sense. And so before we kind of come to some of those constraints that the application developers who were using databases kind of started demanding from the database, right? And kind of being into like the secondary indexes and joins and stuff like that, which is obviously stuff that you would want to do with data. Just a layer before that, right? The technical insight that allowed the ecosystem to start making that availability constraint easier to deal with, right? By changing that from a 3-minute to 3-second time. What were kind of the technical underpinnings of that? Like what changed there to make this 3-minute to 3-second thing possible?
Yeah. I think it has to do with the fundamental way of architecting the distributed systems, right? Cassandra, the way it was architected was there are 3 nodes that are replicating. So, I mean, obviously, scale is an important piece, which means you break data into smaller groups of data shards, right? Like, and so you have to replicate these shards. And so scale requires sharding, and availability and it's like being able to tolerate failures requires replication. So we put the two together. I mean, it's not too many ways to do this. You have to shard data and replicate the shards. So I'm just taking that for granted, right? Now, so now you come to how. The way, for example, Cassandra, we did it was we took the shards and said every shard would live on, say, if you have a replication factor of 3, it lives on 3 nodes. Each of the nodes would deal with, whatever they do. You would write to any of the nodes. They would try to write to a majority. And once they write to a majority, you have quorum. If you read from a majority. If you want consistency, you just read from the local node if you don't, right? So this is the eventual consistent thing.
Right.
The realization here is that there is nobody to enforce sequence. So you could go into the scenario where you have 3 nodes, A, B, C. A and B could have some data. B and C could have some data. C and A could have some other data. And so now you read from A, B, C, you get different pieces of data, right? And reads actually were a pain because now you have to resolve, and even then you don't get transactional consistency. So we were, the majority of the time you don't have failures, so you don't have inconsistency. So, but the majority of the time you still needed to do quorum reads, which means you're doing more work to even get basic levels of consistency, right? So that was, so we changed that in HBase. We said like, look, we cannot have multiple reads. So send all the writes to the current leader, and then when the current leader fails, which is rare, then you go to a new machine and make that guy the leader. Right. And so that was fine. It was great in theory and actually even in practice. But what we did was we took these shards and said the leader can figure out how to replicate the shards to wherever it wants. And when it fails over, the new leader can go and figure out where these shards are. Now, every node would have multiple shards because you don't want the failure of one node because of load to take over this, fail over to the second node, and then that fails on the third node. So you just have dominoes falling over. That's not a good idea. So you have, say, 10 shards on a node. Now, what we said was all of this 10 shards data could kind of be mixed in one node, right? Because you needed the best packed, efficient representation. Not to mention it was hard disks, so you couldn't really do multiple writes. If you know the seek problem on hard disks, you had to, so you had to coalesce them one way or the other. Now, when the node failed over to a new node, like it doesn't fail over to 1, it fails over to 10 other nodes, right? So this 10 shard node that failed over would scatter to 10 because you want each guy to take over 10%, which is a good thing. Now, each of those 10 nodes would need to split and extract the 10% of data it needed from the source node, right? Because, we mix the data. It was all packed for perfect serving and perfect IOPS, right? For hard disks. So, but that extraction of data and the detection of failure, which was done by an external system like Zookeeper, both of those would take time. Right. So however good we made it distributed, we made everybody take up a piece of, we built all this stuff, but it would still be like about 1.5 minutes, 2 minutes to detect the failure because it was done by an external system. And you could have, you don't want flaps all the time. You don't want false positives. Because this is moving data all the time. So it would take about 2.5 minutes and another minute or so to actually split the data and extract at the best that we could get. Right. Then we knew we had reached the limit. And so we needed to go back to the original architecture where the 3 nodes kept data, but the fault tolerance is pushed into those 3 nodes instead of an external system. So take that Zookeeper stuff and push it into the 3 nodes, and every pair of 3 nodes participating
has its own.
So in the hot path, in the data IO path, when a node fails, somebody else is ready to take over because they do their own failure detection. Nobody touches them. And somebody can come in the background and sweep and say, look, this node failed. Let me replace it. Let me re-replicate it. That can be the slow path. So we kind of had to do all of that separation. So that's the underpinning, right, in some sense.
Got it.
And orient this to a multi-zone deployment. That's the other big important thing because there was none.
Got it. And so again, kind of bringing this to kind of from the point of view of somebody that is modeling their data, right? And wants to figure out, how they should think about whether a table should be sharded or not, and what the trade-offs are going to be and stuff like that. What is kind of the orientation that they should take, right? And in modeling that out, right? And perhaps some of this is Yugabyte specific, but also if you can shed light on kind of how people would approach this for different types of distributed databases, even, right?
Yeah.
Like, what are the kind of trade-offs that one would have to explore with different types of databases?
Yeah. So there's, I think we did a blog post on this, which I'm happy to share if it's of interest. But there's really only 4 different ways you can shard data, right? If you go through all of it, there's 4 different ways. We probably did all the 4 and learned the lessons the hard way, so we know which ones work and don't work, not because of theory, but because of practice. The first one, which was used in our memcache tier, was every piece of data is like modulo, like you compute a hash of the key on which you want to shard the data and distribute, and you compute a modulo, you give it a number, and you say, okay, that one goes here, that one goes here. Now, the modulo is computed on the number of machines you have that you want to spread data over. So if you have 10 machines, you compute the hash percentage 10. The remainder,
right,
whatever that number is, it's going to be from 1 to 10. You pick that machine number and you put all the data there, right? The problem with this kind of an approach is, again, we learned it the hard way with the memcache tier, is if you introduce a 11th node, your modulo of every single key is different. So that means your entire data has to scatter gather, right? Completely. So yeah, great, this works great. But if you add a new node, you're kind of screwed. You remove a node, you're completely screwed. So we kind of abandoned that, like that wouldn't really work. Then in Cassandra, we thought like, so the only other option was like, then we thought, okay, the best way to do this is to arrange the database in a ring. And then we're going to give some hash values to each node in the ring. You own something in this range. And we would want these values to fall into that range. Now, if we just hash these values and threw them somewhere, you would lose range comparison. So we said, let us make it a linear hash that is sorted, right? Like, so compute a hash value that preserves the sort order, right? The problem with this was the hash values were really bad and the distribution was horrible. And so you'd have one node with 10 times the data of the second node. And so that just defeats everything. Like, you're neither getting the distribution nor are you getting the range. So you're just in the middle of nowhere. So then we went to the third model of hashing, which is pure hash, which is just like compute a random hash and spray it and lose the sort order property because it's not always important. Right? So this worked great for a majority of use cases, yet there were some use cases that needed that sort order. Right? So then we said, like, in those cases, it's impossible to predict. Like, for example, if I said, like, there's a bunch of students that are, that have, that gave an examination and they got marks from, say, 0 to 100, theoretically. That's the total. Why don't you pre-split this data? You don't know the distribution. There's no way you can find out, because maybe 0 to 50, there's barely anybody. And then there's, but that's the real data set, though the theoretical value is 0 to 100. There's no way to predict this. So what we said was this has to dynamically split out, right? Now, natural data sets have a tendency to have hotspots if you preserve the sort order. If you disperse, you lose the hotspots, but you also lose the ability to do the querying in ranges, right? So one of the explicit decisions we did in YugabyteDB is to have both forms of sharding available, very easily specifiable at the create table level. So distribute for removing hotspots, but preserve order if you want to do range queries. So always opt to distribute if you can. And if you cannot, for the minority of workloads that need the sequential scan or the range scans on the primary key, keep that. So I would say this applies across all databases. So just look for distribution to avoid hotspots and range scans to preserve the sequential access. Yeah.
Oh, got it. And just from a just for folks on kind of understanding typical workloads or examples of workloads which are great examples of places where you can distribute to remove hotspots, where that is a mandatory requirement, and places where range queries become important. Can you give us a few examples?
Yeah, absolutely. So most of the naturally occurring scale-based workloads tend to be distribution oriented. Like, let's say you have a bunch of users in an account, right? And you want to look up a user's email address. You give them an ID. You want user ID to email, user ID to password, user ID to their profile. All of this is hash oriented, right? You're really not doing anything else, right? Now think of a different workload where you go to the same, like, let's say an e-commerce site, and you want to find out all things offered by a seller that's between $100 and $200. Okay, so you're now looking for items that are between 100 and 200 in price. This is not because there's an infinite number of values between 100 and 200. I mean, not infinite, but you see there's too many, right? Like all the decimal points, everything you got to include. So you cannot practically go and fetch data from so many. You really have to sort it in a manner where you're able to get
variable.
Yeah, exactly. So that's one example. So this is a simple couple of examples.
And yeah, would messages, for example, also be in the range query side because you're looking at fetching messages of a particular type? Is that what it would map to?
Sorry, could you repeat the question?
Would messages, for example, like chat messages, for example, map to this kind of to the second category of the range query?
Messages, it depends on the way you architect it. I would say if you're thinking about Facebook scale, it's absolutely hash based because so here's what happens, right? There's two ways to think about it. So you and I, let's say I send you a message and or I send you and two other people a message, right? And that's stored in a message table. And all of us reference that. Let's take that architecture for a second. Now that's not the only message in your inbox. You will have 50 messages, and those 50 messages are not the same 50 messages in my inbox, right? Which means over time, I will have pointers to messages all over the message database across all machines and shards, and you will have the same, right? Now, if one machine goes down, what is your experience? You would lose 2 or 3 of your 50 messages, and I would lose 2 or 3 of my 50 or 100 messages. And it feels to the user like, what is this system? It's highly unreliable. Like it's dropping messages randomly. People would understand your entire inbox being lost because, oh yeah, they're working on it. They'll get it up, right? But if you lose a couple of messages, that's really concerning, right? So you need to denormalize. That's the only way to do it if you want to build a good product. And if you denormalize, then you never access outside the user and join. So this was actually a story of Messenger. This is exactly what we ended up doing.
Got it. So you kind of absorb that complexity on the right side and then just duplicate those inboxes and shard that along with where the user's data is.
Exactly. But if we were to do it today, we could use, like, for example, a distributed SQL database like Yugabyte. You could actually do a second table because it gives you high availability. Your outage is not big. However, even in that case, the message table is still going to be scattered because what are the 10 messages in your inbox? They're going to change over time and they're going to be all over the place. So you have to do a scatter to fetch those 10, 20 messages, right?
Interesting. I think one of the other constraints when from a modeling point of view, right? If I think about like, here's a table, how do I want to shard it? Another constraint is also thinking about what is this data going to be frequently joined with, which kind of is being from exactly what you're saying with denormalizing, right? And that also places a constraint because the way that the sharding patterns that I would want for data that are frequently kind of joined together should be similar, right? Or perhaps even exactly the same. So that they
as far as the distribution goes, as far as the distribution nodes, after that you can sort differently, you can do other clever things.
Right. But so then I think that becomes another factor for people thinking about from the kind of data modeling point of view, right? No, that's awesome. Just taking a quick pause to take some of the questions that we had in chat. So Nikhil had a question on thanking Karthik, which is great. But then also, how long will it take for Hasura to integrate with Cassandra? This is a good question. If there isn't already, please do open up a GitHub issue so that the product and engineering folks can also start interacting on that. We're doing some interesting work on being able to kind of bring in support for a bunch of these different types of databases sooner than later. It's a fairly different approach from what we were doing last year. So, potentially good news there. But if you can open up a GitHub issue on the repo, then we'd love to chat about it in case there isn't one already. But then, Karthik, I think question for you from Nishad is, how would you compare Yugabyte to Vitess? And so before this turns into a vendor A versus vendor B conversation, maybe just kind of just talk about it from a kind of architectural approach, right?
Yeah, that's all I'm going to do. Yeah, that's all.
Yeah, just from that point of view, talking about kind of key trade-off differences and again, importantly, from the point of view of for somebody doing a data modeling exercise, right? What would you kind of encourage them to think about when approaching a distributed system that is architected like Vitess versus what would you tell the data modeler to think about when they're approaching that their workload Yugabyte, right? Maybe that lens would be helpful.
Yeah, exactly. No, yeah, I'm going to keep it very technical because no need to definitely no need to argue about the vendor side of it. So I think the strategies are very different. Vitess, the way it works at the highest level is it retains all of it's MySQL underneath. It's the same MySQL underneath as your regular MySQL. And it builds a layer on top that will distribute your data and your queries across these MySQL instances that you have below, right? So you can think of Vitess as a sharding layer on top of MySQL databases, right? So if you are querying something inside a shard, it'll push that query down all the way. If you are doing something across shards, well, it'll do something, but that's not its strong point, right? So to exactly the data modeling question that Tanmay and I were just discussing, if you are doing hash sharding where you want to move your data hashed or like just disper it across nodes, you don't want to sort or compare across the different shards a particular key, then Vitess is great. It'll do a great job. The advantage you get with Vitess is it is the same MySQL that you've used for years and years. So it'll push down all the queries and get all of that done. Now, so that means in some sense, Vitess keeps the lower part of MySQL the same and builds a routing layer and a distribution layer on top. Yugabyte's kind of the opposite. Yugabyte keeps the upper part, in this case Postgres, but nevertheless another relational database. So what Yugabyte does is it takes Postgres and stretches it across nodes. So it doesn't split the data across nodes and keeps it, and that's not the intent. The idea is to take the single relational database and stretch it across nodes. And that means we keep the upper portion of Postgres the same, the query processing layer, and rebuild the lower portion, right? Which is the exact opposite of what Vitess does. They keep the lower and rebuild the upper. So what does that mean? That means that stuff that is going across nodes, like your range sort to maintain your sort order across keys, that's easy. Your global transactions across shards, all of those are easy. But whatever happens inside a shard, we're not as good at it as Vitess would be, because it's the same MySQL that you push into a very efficient single node database. And we are more about distribution, right? So we will push down as much as we can, but we redo the distribution and representation of data to be more friendly towards scale out and HA and resilience and all of that. So hopefully that gives you, so the difference here, HA scale out, that's the focus point, and treating the whole cluster of nodes as a single database. There, it's about treating it as a set of databases integrated through a sharding layer.
Got it. Yeah, that makes sense. And I think the analog to that, again, in the kind of distributed SQL ecosystem is perhaps the Citus and the Hyperscale is kind of that similar idea of the lower half of Postgres remaining the same and distributing data across lower half of Postgres.
Exactly. Hyperscale and Citus is the same, exactly, for the Postgres ecosystem. That's right.
Yeah. No, that's super helpful. That makes sense. So I think then, kind of thinking about this idea from an application development standpoint, right? When we think about what has changed on that side of the ecosystem over the last few years, what is kind of seeming to happen is that as compute and the ability to kind of deploy has become so much easier from a code and application code point of view towards the edge, right? What has happened is that as long as our code does not require any centralized state, the entire life cycle of that, the scalability, the availability, the speed with which you can iterate on that is just massively different from what we had 10 years ago, right? When we were doing server-side development, because now your compute is kind of on the edge, meaning it could be on services or workers or functions that are running on the edge. In fact, we're seeing early days of that compute even being spread across a browser and a mobile application and a worker on the edge, right? That's starting to happen in a way that's transparent in a way that like the developer doesn't even have to care about it, right? They're like, yeah, I'm just writing this code, and a part of this code that runs in the browser can just run as a function on the edge as well, right? So that you're kind of splitting that compute between a device and a cloud vendor at the edge, right? So that innovation has kind of greatly increased the capability for developers to be able to build those applications quickly. But kind of where that story still needs to be plugged in is that ability for people at the edge to be able to access that centralized data, because the reason why it's a common application is because there is some centralized data that we're exchanging and operating on, right? Otherwise, we wouldn't have a single application that we're working on in that sense, right? Not all applications can be truly distributed, right? So, so in that case, kind of what the challenges then become for these developers, and if we take an extreme point of view to say, let's say a few years from now, nobody's doing server-side development, but you're only doing close to the data development, like data modeling.
Yeah.
You're only doing either data modeling and logic that needs to reside as close to that centralized data as possible, or you're writing application code that is on the edge, right? And everything else just works, right? From kind of just unpacking that a little bit, right? What properties we would want from the system, as and speaking on kind of from the behalf of like a developer on the edge, I would want to make sure that that access to data is kind of secure and performant and stuff like that. So you need an API layer, and that's kind of the problem that we're solving at Hasura.
Yes,
providing that GraphQL API layer that's creating that boundary which is performant and secure to access the centralized data, which is fine. But other things other properties that these developers now need from their centralized kind of data store becomes basically ensuring kind of that availability that we've been talking about, right? The ability to scale that data, to shard that data, which we've talked about. But then I think also this idea of, I think, two interesting things there. One is geo replication, right?
Yeah.
And being able to spread that around with multiple AZs. That kind of becomes one interesting property as we start thinking about if my application and compute is truly at the edge and can be consumed conveniently by developers wherever they are. I would like them to be able to transact with whatever data they can, which is close to them, right?
Yep.
And that becomes that becomes one property, right? The second property also is that when I start thinking about transactional logic and logic that needs to live close to the database, and here I'm thinking about things like when we talk about the relational database part of an RDBMS, we're talking about indexes, we're talking about joins, we're talking about transactions. Technically, this logic could be done at the application layer as well, but it's just much better for all of that to be closer to the data layer, right? So how is the ecosystem, how are you thinking about these two aspects, right? First is a geo-replication aspect. Is that significantly different from replication? What are the things to think through there, speed of light concerns, etc. What is kind of the set of things to think about there? And then maybe we'll talk a little bit about that desired relational database side of things, which gives you a convenient way to think about logic that should be close to the data that you want to keep close to the data layer, right? So let's unpack that a little bit.
Yeah, no, these are great questions. I think this is the direction of future app development, right? This is really where it's headed. So I would say replication is actually a big piece of distributed database. I mean, it's distributed, it has to replicate something. But if you do it naively, it obviously starts hampering app development the way you want it. Now, even in your example, right, where there's a central repository of data stored, and there's like a whole edge where the fast transaction processing happens, there's actually going to be some necessity to shuttle data back and forth, some percentage of it, not the whole thing, right? Like maybe a couple of simple examples, right? Like you have a bunch of, let's say, routers that you have deployed all over the place, and you have a central configuration, right? You want to see what the router's configuration are, but you might want to change it and you want it pushed all over the place, right? Very, very simple stuff. Just these two examples, right? So pulling the configuration that's currently installed on the routers to a central location is the opposite in some sense, where all the changes that you make on the edge actually reflect on the routers, but it then gets sent to a central location and you just get a view, right? The view is important, but it's not, if it's like partitioned for a while, it doesn't matter, right? Whereas the opposite, like when you change it in the central location and want it pushed out, it's okay that it's partitioned for a while, but it eventually has to make its way out. You don't care about a split-second transaction. You want the centralized thing to accept it and push it out, right? So if you start thinking about these are just a couple of examples. There's a lot of such examples, right? The trade-offs really come to, obviously, you need scale, operational ease, make it simple, make the API powerful enough to build your application. All of those constraints are just like table stakes. So you need it on both sides, right? But additionally, what you are really trading off is your availability and resiliency characteristics of each of these deployments. So, which is really how the failover happens and all of that, versus the performance and like your latency of access and your performance and how much data can flow, versus the consistency of data, the transactional consistency. How a point in time, is it an older stale piece? Is it like the current piece? All of that stuff. So I'd say you're really making a trade-off between those three. Again, availability / resilience, between performance / latency, and between consistency / transactional nature, right? So those are the three things that you're really trading off, right? Like just like you can kind of think of it as an alternative cap theorem for the edge, right? And we have to come up with a nice name for it, I guess. But those are the three things really, right? Now, it bleeds into your second point, because One of these patterns could be such that, you might just want to say, I want to deploy a relational database on every edge, right? As an example. And every time I deploy it, I have the same schema for every edge location, the same schema. Now, I want to be able to access data from the remote location if possible. And I totally understand it'll be slow and bad. I understand that, but those are rare cases. But the majority of the case, I want my operational app to go against the local region most of the time, right? And if an application moves elsewhere, I should be able to move the data to that new location, right? And now, what is the complexity of building this into the app? Well, the app has to now be aware of the database topology. This node, that node, this region, this machine, this is decommissioned, that is new, just too many things going on, right? As opposed to if you can push it into the database with some sort of SLA, it becomes a lot easier. So we call this geo-partitioning, for example, right? Where you're able to get the same database in multiple places stitched together. The database will do its best to keep data local and do local accesses. But hey, if you have to do remote accesses, so be it, right? So there's a lot of building blocks that go into this. There's 4 fundamental forms of replication that we have identified at Yugabyte, and looks complete, but who knows? Time will tell. Synchronous, asynchronous, bidirectional, unidirectional, all of that stuff. There's read replica, so write in one place, but read from a read path
from the other place.
Yeah, and geopartitioning, where you keep the data itself partitioned in different locations. So with these, there's a number of interesting ways in which they interplay inside a single application to get you your, like in our example of the router, it's 2 different, right? So yeah.
Got it. No, that makes sense. And so depending on the use case or depending on the piece of data, I can think about what is the ideal replication mechanism
at a per table level, at a per database level, a schema level, at whatever, a group of tables level,
whatever that
yeah. And I think this question actually gets super interesting if I turn it back to you, right, from the layer just above, and ask you, how are you thinking about it? Because I mean, this is an interesting area.
The very short answer for developers at this layer is that we don't want to think about it. we just want the barest, the simplest set of primitives that can be attached to the modeling side of things, right? Like, for example, saying that if you think about, like, from a modeling point of view, I'm modeling a table, right? Thinking about the constraints that I have while modeling this table, right? Everything from sharding to the nature, the kind of replication that I want to have for that table, right? Putting those primitives together and enforcing a small cognitive overload at the modeling layer is where the edge developers would like it to stop, right? And not have to go layer below that. So when we think about absorbing this complexity at the Hasura layer, right? For us, it kind of becomes, and it takes us in the direction of thinking about when we help our users model things or bring in models from decentralized data sources or distributed sources, right? We want to absorb that complexity around topology, around modeling, and expose that as primitives that are being added alongside the data modeling piece, right? So that again, together, this API layer and the data layer is then exposing something easy to use for the application developers building at the edge, right? So that they don't have to care about the how of it working, right? And it's as simple and small a set of logical primitives that makes this happen, right? And to your point, I think at a technical level, dealing with these problems around topology, dealing with these problems around what kind of replication to have, etc., is really just a matter of making sure that people are making good choices, and they're able to move from one choice to another without
on the fly,
right? Like oops, I chose a wrong sharding mechanism. What do I do now, right?
Or just build an index and drop the old one, and that's it. Yeah, exactly.
Right. That's the level that you want to be thinking at, essentially, right? Or even things like, for example, one of the things that might become necessary for certain kind of workloads is having a globally or a pseudo globally sequential ID. That is then kind of provided, right? Which there's so many different ways of doing and solving for that problem, right? But that's a primitive that unlocks a lot of use cases, right? And makes it easy for people to think about a lot of different kinds of use cases, right? So solving those kinds of, I would call them modeling challenges, and mapping a use case to the right way that people model, right? I think there's a huge amount of work that needs to be done there, right? Both at a technical level, at an education level, at a creating resources and talking about this, right? So I think there's a tremendous amount of work there. moving kind of, I give you have the last 5 minutes now, and so perhaps we'll take some questions. Yeah, Pradeep agrees with me, which is true. We don't want to think about this, right, Pradeep? This is true.
We don't want to, yeah.
Cool. Just looking at a few of the questions. Nikhil had a question on how to deal with kind of large amounts of data and thinking through what kind of database is optimal. Yeah, Karthik, maybe, I mean, I guess that's a super broad question. So
yeah,
maybe
I would say
dimensions of thinking about it.
Yeah, the highest level dimension is what is the application going to do? Is it an analytic application? Is it like a transactional application? So the difference is, in an analytic application, you want to do real time. You want to give one query which analyzes all the data and gets you back the nuggets, right? Like, for example, if I'm running an e-commerce store, how many people in North America visited a particular shoes page, for example, between 15 and 40 years and stayed there for more than 30 seconds? Like, that's a completely analytical query. It's real-time interactive. You have to probably look at a ton of data. So versus if you actually want to do your ordering system, your login system, your shopping cart, that's very transactional, right? All of these touch small amounts of data, but they have to be very quick. So at the highest level, you probably have to decide that, right? And then the second thing you have to decide is your nature of your data. Is it, how critical is it? How bad is it if you lose data? Are you okay with, like, is it like, for example, time series data that you get from a sensor and you lose a little bit and you're like, fine, that's okay, it'll refill itself? Or is this like used to generate an alert or an event, or it's actually like a billing order and you absolutely cannot lose it? And is this like retained forever, or do you have to purge data automatically? So those are some of the things I would say, like, that you have to start from and then work your way down which databases have support for those type of features.
Yeah, and I would add to that also is the kind of the nature of the way that you want to think about the reads and writes kind of from a modeling and application design point of view, right? Like, for example, do you want fast reads? Are the reads going to involve lots of joins or not, right? And what latency you want there? And then also absorbing that write complexity, right? Do you want to have like a distributed transaction running, or you want to have single transaction running and then trigger and eventually consistent
like a CQRS pattern,
like a CQRS type pattern, right? So those then also kind of impose some constraints. But moving on to another question by Adil, which is what about different database schemas for different regions and having different parts of your database schema in different edge locations?
Yeah, this is absolutely possible. I think this is absolutely possible, right? I think you would say the same thing, Tanmay. It's absolutely possible. I think the complexity becomes one of now management, right? Of all the different edges, which look different in nature rather than similar. It's a far easier to manage a similar looking edge deployment than different. But yeah, I think, probably nothing inherent about it.
Yeah. No, that's, I think the one of the pieces there was, for thinking through these kinds of things, the lens that I tend to take is less of a application development lens, but more of a ops and ownership lens, right? Which is that, why do you have different database schemas from an operational or an ownership point of view? That's probably driving that decision more than a technical decision of, does my data need to be split in different schemas or not, right? Exactly. And so that can then drive that decision making. Just the last question for our session today. For a startup, is it better to start with a single node Postgres and then migrate to Yugabyte different data?
Yeah, the $1 million question, man. The $1 million question. I wouldn't be very good if I told you to start with a single node Postgres, but that's what I'm going to say, because it's so in reality, I mean, this is how it goes, right? A distributed database is actually designed for that, with distributed data, right? And so if there's at least 3 properties you have to consider. Always available, like resilience and availability, never lose your data. The second aspect is scale, whether in the future or at some point. The third one is replicating data all over the place, right? Like all kinds of replication we talked about. If at least one of these 3 is not interesting, then you should absolutely stick with Postgres. There's no reason to, because Postgres is really good at what it does as a single node database. That's why we picked Postgres, right, as the API layer, and now we're going below to actually figure out how to get it distributed. This is also a point in time answer. So we are working on handling smaller data sets better and better over time. So we would love to work with you, obviously, if you like, if you're interested, to figure out how we can optimize it. And we are building a number of features, again, transparent, so users don't have to think about it, but it will really handle data well at the lower end of the spectrum. But if you're talking really, really tiny end of the spectrum, we're never going to be able to beat Postgres. So the smaller the data, the more gap there'll be between something like a Postgres and Yugabyte. And as the data volume starts to grow, even to moderate amounts, then that will kind of even itself out, and you'll get the value out of Yugabyte, right? The trade-off
Yeah.
is you'll have to migrate at some point if you reach there. So that's really the.
Yeah.
It's not an easy answer. So
no, it's not, and I think it's to a degree it's a similar kind of maybe the analog here is similar to should I use SQLite or Postgres?
Postgres,
right?
yes, it's one step up.
That exactly. It's like basically if you were having this conversation, say in the 90s, where should I use SQLite or should I use Postgres? And you'll be like, SQLite will beat the pants of Postgres for certain types of workloads, depending on a particular size of data and constraint of data, right? We are now in an ecosystem that is transitioning through that journey of moving from a single node database to multi-node databases. And exactly to what Karthik said, it's a little bit point in time, because it's a little bit of like the technology will keep evolving to help bridge that gap and keep kind of gradually making that single node gap to multi-node gap almost seamless. But then also the tooling in the ecosystem, from the point of view of vendors like Yugabyte, but also from the point of view of API layers like Hasura, is to make that transition easy as well. To say that, start off with that Postgres, and you're noticing that one model or one set of models are going crazy and they need that scale out, making that migration easy to say, can I keep like 90% of my tables in Postgres and not have to worry about that migration, but take the 10% and move that into Yugabyte, and then start putting my new workload there. That starts to become a feasible thing to do, right? And I think the industry is going to kind of keep moving there. So, but that's I think the long and short of this session. It was super fun, Yugabyte, talking about Yugabyte, Karthik, and just learning from your experiences there. I think for other, I love getting into kind of technical nitty-gritty conversations. There's a bunch of other questions that we've not been able to answer, and so I think feel free to reach out to Karthik. He hangs out on Twitter and LinkedIn as well, so he'll be available there. And feel free to reach out to me on Twitter as well. We'll be circulating recording and our coordinates and stuff like that after this conversation. And thanks a lot for being here, folks.
Yeah, thank you, folks. Thanks, Tanmay.
Bye, everybody. Bye, Karthik.
Bye.